In question 5, we're told that Tom makes annual deposits of $1,000 into a bank account that earns 4% annual interest. If he does this at the beginning of the year for 49 years, how much will be in the account at the end of the 49th year? And show work to justify our conclusion. And this is again a geometric series. So if we just write down a formula based on the story, our total money, well, the first year we make a $1,000 deposit. And it grows by 4% every year, so multiplied by 1.04 for every year for 49 years, so to the 49th power. And then the previous year, the next year he deposits $1,000, and it grows by 1.4%, but it's only in the bank for 48 years, and so on. And then the very last year he puts in $1,000, and it's just in the bank for 1 year to earn interest. So if I factor out the 1,000 times 1.04, then I'm left with 1 plus then I can reorder these terms to be more in the order that we're used to seeing them. So I'll put the high powers at the end. So that's really 1,000 times 1.04. I'm just going to write them backwards. Then to see it as a geometric series, I'm just going to pull out the 1,000 times 1.04 to make that first term a 1. So then I have 1 to the 48th is my last power because I pulled out one of the 1.04s. So then if I write the stuff that's in the brackets, that's a geometric series, I can use my finite geometric series formula. So I get 1,000 times 1.04 times 1 over 1 minus 1.04 to the 49th over 1 minus 1.04. Again, because that exponent in the finite geometric sum formula for the ratio 1 minus 1.04 to the exponent, that exponent is 1 more than the power in our last term. So our last term's power was 48, so that exponent is 49. And then that's just arithmetic. And when I put all of that into my calculator, I got $151,667.08. Now part B says, now suppose that he does this at the beginning of the year for 50 years, write a single finite geometric series that gives the amount of money in Tom's account right after he makes the last deposit, and then use our formula for the sum of a geometric series to find the value in his account. So because it wants me to write things as a geometric series, I'm just going to start from scratch instead of trying to relate it to part A right now. So in this case, my total money would be, spelt total wrong, total money would be, well, he's putting in $1,000 at the beginning of the year for 50 years, and I want to know the value right after he makes the very last deposit. So the first deposit, he puts it in at the beginning of the year for 50 years, but at the very beginning of the 50th year, that's when I'm going to take the money out of the bank. So the money only sits in the bank for 49 years. So the first $1,000 is only in the bank for 49 years, and then I have $1,000 that's in the bank for 48 years. And then my last deposit that I put in doesn't earn any interest, right? There's no 1.04 exponent because I want to know right after I make the last deposit, how much money do I have? So then, again, just reordering the terms to be in our more standard order. I'll factor out 1,000 this time because that's my first term, and I get 1 plus 1,000 times 1.04 to the 49th because I didn't factor out any 1.04 this time, right? I just factored out 1,000. And then if I write that as a finite geometric sum, the formula would be 1 minus 1.04 to the 50th over 1 minus 1.04. And then when I put that into my calculator, I got 152,667.08. which in part C, we're supposed to compare those two answers and talk about why they make sense. Well, if you notice, if you look at those two answers, part B's answer is just exactly 1,000 more than the answer to part A, which completely makes sense because the only difference in part B and part A is that I make a $1,000 deposit that doesn't earn any interest. So part B's answer should be exactly 1,000 more than the answer to part A. And that's what we saw when we did both of them using kind of our rules for geometric series.